Hi everyone, and welcome back from the lunch break. I'm Francesco Perticarari. If you weren't here this morning, I run Roundabout Ventures, investing in pre-seed, early seed, deep tech. And today I'm joined by Richard, Max, and Waseem, and I'm going to let them introduce themselves too. So thanks for joining us after lunch. Let's go this way. Richard, why don't you tell everybody what you do at ORCA?
Thank you. Yeah, so nice to meet you all. My name's Richard Murray. I'm chief exec and co-founder of a company called ORCA Computing. We build photonic quantum computing systems. Background all over the place. I spent time in academia, I spent time as a consultant, in government, in big companies, small companies, and everything else in between.
And all the in-betweens. Max.
Hi, I'm Sich. I'm CEO and co-founder of Aegiq. So we build, again, quantum photonics, also for quantum communication, sensing, can be used for computing as well. So we'll build that toolkit to kind of bring quantum closer to life and to everyday usage. Background physics, background economics, done quite a few other things before starting Aegiq, so I think it's a really exciting time to dive into the deep end of the deep tech.
Waseem.
Yeah, so my name is Waseem, it's working?
Yes.
Yeah. I am with a company called Quantinuum. Quantinuum is the world's largest quantum computing company. It's an amalgamation of two companies, Honeywell Quantum Solutions and Cambridge Quantum, and I was part of the founding team at Cambridge Quantum in 2014. Since then, we've developed an integrated company in quantum computing hardware and also in quantum computing software, where we're looking at specific solutions in cybersecurity, chemistry, machine learning, and natural language processing. The reason why we do it, because we think quantum computing will fundamentally transform the way we live, and we want to be a part of it.
Cool, great. So, of course, I think you figured out by the title and by the introduction of everybody, we're going to talk about quantum computing and quantum technologies. And just before this event, we had a chat over Zoom about what we're going to discuss today. And I actually remember one topic that was getting pretty hot in the discussion in terms of quantum technology. Sounds like a very big esoteric word, and of course, you know, we pretty much all believe in the future potential of these technologies. But how far away is this future, and what's happening between now and then? You know, is it going to be this black box of pure belief that something amazing is going to come out at the end, and you're just going to have to keep throwing money and research into it, or is it more of a gradual process that's going to get us there, both in terms of results for everyday people's life and obviously commercial results? So Waseem, why don't we go in reverse? What do you think on that topic?
In terms of timing, I don't know. I mean, is it going to be 2 years, 3 years, 5, 10, 15? Frankly speaking, I don't think anybody does. This is something that, it's a process that we have to go through. But our belief, or my belief, is that it is inevitable. There is a huge amount of investment of capital, both financial and human, going into this effort. So I think, given where we are in the cycle, I think we should see tremendous progress and advances over the next few years. I don't think there's one particular on-off switch where you say, okay, well, the technology is here now. It's never that way. So I think it's going to be a gradual process. There will be certain inflection points where new innovations and technologies come to the fore, which then allow the advancement to take place. So, you know, for example, the work that these guys are doing and their teams are doing, and our teams, are all part of a concerted effort to get to the next stage. And you've seen that in the past with all technologies. There never really has been an on-off switch.
Well, yeah, I'd like to kind of agree on that one. Especially, I mean, are we there with digital technology yet or not? I mean, we still have, you know, digital transformation teams in lots of places. So it's not indeed an on-off process. Moreover, it's not even a linear process. So we kind of, with like, I don't know, digital and all the kind of tech that we currently use, we kind of got used to the fact that a new iPhone comes every year, like the iOS or like whatever software is updating cycle is twice a year or like once in so many years, and it's very predictable, and we kind of got spoiled with that a little bit. So most of other technologies are non-linear, and you kind of can have a breakthrough, then it's kind of quieter a little bit. It doesn't mean that work isn't happening, but it's going on there. And I think you have to also be careful about defining KPIs there, also KPIs for industry or for yourself personally. And it shouldn't be purely based on the existing models that we have, or like playbooks that we have with, say, digital. So it's different.
Maybe if I just chip in and add some numbers to support the things you guys were saying. So at the moment, sort of quantum computers aren't useful, broadly speaking. I think everyone pretty much accepts that. Quantum computers at the moment have anywhere between a few hundred qubits, which is sort of what everyone admits is like a standard of measurement to work out how good systems are. So a few hundred qubits. So sort of bear that in mind for a second. In order to get to what everyone thinks is the holy grail of quantum computing, which is a system that can run error correction. So you imagine you want to run a big algorithm, as with any normal computer, you need to run error correction codes. The same is true with a quantum computer. So error-corrected quantum computing is the thing that will allow us to change the way we model drugs, maybe break RSA encryption, although those are applications. That system, to do that, requires something of the order of at least a million qubits to run those types of algorithms. So that gives you an idea about where the holy grail, how far we are away from the holy grail of quantum computing. Like 100 qubits today, million qubits, to get to this holy grail point. But what's really cool at the moment is this hotly debated topic about how useful systems can be today. And so what certain companies are doing, Quantinuum I think are doing a bit of this, so ORCA, looking at hybrid quantum classical systems. So not rely on the quantum computer for everything, you'll solve your whole problem on just the quantum computer, but putting a quantum computer next to a sort of pretty impressive GPU cluster, so quite an advanced classical computing system. And if you do that type of thing, if you play those tricks, quantum systems can potentially provide something useful sooner. So imagine now in this near-term regime, and we'll say this is really being discussed and debated and researched all the time, and to Waseem's point, any day a breakthrough could happen. If you try and rely on your quantum computer for only the most difficult part of the problem, so let your existing computing system solve most of the rest of the problem, and then only rely on your quantum computer for the thing which is hardest, like where the information density is highest, the complexity is so high, your classical computer is struggling. Those are the types of near-term ground where things could happen, and that could be any day now, next few years, I'd say.
Cool. And then any examples that you guys are either working on yourself right now, or that you're going to or that you're aware of in the industry that could be affected by exactly this sort of let's say, short to medium term solution, as opposed to the full quantum supremacies that we all agree it's not going to happen tomorrow or next year.
Yeah, I'll just jump in quick.
Yeah.
So for us, it's machine learning. So trying to use quantum computing systems as a replacement for certain layers in your neural network. So you're going to build up a big, deep neural network. Some of those layers can be replaced with a quantum layer, and so that could provide some advantage. So for us, it's machine learning, I think.
Cool. I think for us, we take slightly different approach. I mean, it's complementing approach. It's not like we would disagree about something, but it's about enabling having really high efficiency hardware. I think, error correction, there's two ways you can deal with it. You either have less errors, and then you can scale better, or you have better error correction code. So we take it and say, well, let's build something that is has got less errors, and we just build those, tools for people to just do this. So yeah, in a way, it's not a computer per se, but it's really enabling the ecosystem, the infrastructure to exist. And it's really important to point out that there's no one single entity that can pull through quantum technology.
Yeah, and
So
actually you
it's-
touched on a good point there, because there is the whole supply chain problem, right? Quantum is not a single thing, and Waseem, you mentioned you guys being already a merger, and in a way also with a spinning out department from a corporate that is established doing other stuff that is not quantum. So how do you see the ecosystem coming together? Because of course, Max might be manufacturing a semiconductor part, and then ORCA might be developing a system that brings it together. Like, how do you see the ecosystem basically coming together, and what's needed for that to come to fruition?
I think we work very closely with all quantum computing companies. So the approach we've taken, despite integrating hardware and software, is we have a platform agnostic approach, which means that we develop solutions and software which can effectively run on any platform or all major platforms. So that's a view we take, just work with everybody in the ecosystem. And in addition to that, we work very closely with clients. So everything we do is with an end user. So for example, in cybersecurity, we've developed a product and a solution that we are now deploying with major organizations and infrastructure providers to provide enhanced cybersecurity today and also post-quantum cybersecurity. In quantum chemistry, we work with large entities working on large-scale problems. So for example, in carbon sequestration, in looking, so that's with Total Energies. With Nippon Steel, we look at the formation of new alloys. With Roche, we're looking at Alzheimer's disease. So there's a wide variety of use cases in machine learning. It's optimization challenges with companies like DHL or Deutsche Bahn, or again, Nippon Steel as well, looking at their production scheduling. So these are large-scale companies with large problems that could potentially be solved by quantum computers. They take a long-term view. So, for example, when Total looks at carbon sequestration, it's got a 20, 30-year program for carbon reduction. And so they'll look at quantum computers, maybe not today, maybe not in 2 years' time or 3 years' time, but maybe in 5 or 10 or 15 years' time as to how they could solve that problem at that point. Mm-hmm. But they start experimenting now. So that's an important part of our ecosystem, to work with end users who have a use case which will be amenable to quantum computers.
Okay, and on that, by the way, is there anybody in the room that is either building or investing in quantum-related technologies, or at least open to the idea? Like, come on, show of hands. Okay, so there has been a few articles going around basically saying that we're all morons because we're putting money into like a hyped industry that has got a lot of promises but it's not going to deliver on time. Are we morons? And if not, why not?
Are you morons? No. No, I mean, it's, well, let me backtrack. The business case, the reason why everyone's so excited about quantum computing is because you don't have to look around very hard to find loads of use cases like the ones Waseem just mentioned, where current computing systems just do not cut it. And maybe slightly more flippantly, I always just sort of talk about how poor, I'm not sure if I'm allowed to say this in this forum, how poor AI is at the moment. You know, if you actually try and rely on driverless cars, there are all those horrible YouTube videos of Teslas crashing into things. And AI just could be a lot better, it could be a lot more human.
Energy efficient.
And not to mention energy efficiency. So there's a massive need for new computing hardware, and lots of people are solving that on the classical side, GraphCore and other types of companies developing new chipsets and things. And then quantum is sort of the same thing, but another level, like a complete reinvention of how we're thinking about computers for modern day problems. So, come on, if that's not worthwhile as humans or investors investing in, then I don't know what else is.
And in terms of besides the capital then, what do you think are aspects of the ecosystem that you'd like to see improved? Actually, I remember in our chats we were discussing.
Before we get on that, I'd like to jump on one other thing, is because when people, I think, quite often if you start a sentence like quantum, you quite often add computing to it. Now, computing is not the only thing which is quantum.
Good point.
I mean, it's a big driver, I think, maybe the biggest, but nevertheless, it integrates with communication, cybersecurity, and it has different aspects in cybersecurity. You know, the computational, the physical layer, security, even sensing. And it's kind of a hybrid in a way. And like we have hybrids today. So your home router, is it a computer or the communication device?
Mm-hmm.
It's kind of both at the same time. So you don't have to forget about this bit and how computing actually impacts this. And I think that's a really important thing for the ecosystem as well. Because those things, they evolve together. Like better sensors, for example, they contribute to better, production control. Can they feed into a communication network that sends that input into a computing device for, an on-time optimization for something that used to take, a year.
Mm-hmm. Yeah, no, definitely. There's definitely the whole world of quantum that is not computing, for sensing and everything, and that's health, that's energy, but in terms of then, again, what else do you need to develop further all of these verticals, not just computing? What do you think are strong aspects to today's ecosystem? I guess one, at least investors are looking at this and governments are, but what are potential shortcomings? And I remember, for example, in our chats before the event, we were seeing how maybe the US has created a little bit of more of a united framework. China, obviously, because it's dictatorial and, at least they have a vision. Europe is still a little bit all over the place in terms of ecosystem. So do you think there are challenges with hubs being distributed? Do you think there are solutions to that? Are there other challenges that we need to overcome to create a strong, also European quantum ecosystem?
Just going back to your point about the investment, the trends and the morons, and
in the full.
I don't think there has been any technology in the past that has received so much governmental interest. You can maybe go back to the Manhattan Project. So it's a serious industry. There's some serious players. It's a US government. It's all the major governments in Europe, Russia, India, Japan, China, and the list goes on. Australia. Each one of these countries has a national computing program. And then you layer that with Google, Microsoft, IBM, many other corporates, and then the financial investors from the VC space as well. So this technology is going to receive more and more interest going forward. And I think it's just a start. We'll see a lot of intensity in terms of the competition for talent, for nationalization of the technology. So,
how do you balance that out then? Again, if you want to create a strong UK, European quantum ecosystem, how can we make it better? What's potentially there that is not yet, or it could get better?
Partnerships definitely help. And as I mentioned before, working very closely with industry and with those companies that have access to the data sets, that know more about the subject matter than anybody else does, and who want to then invest time, effort, and capital towards solving that particular problem. So with that in mind, and if you back that with governmental capital, financial capital, I think you do have then the foundations for a strong ecosystem. But there's a big piece which I haven't mentioned, which Richard will touch upon. Ultimately, it comes down to people. So if you don't invest in the science, the technology, and the education of those individuals, you won't get anything. But Richard, I'm sure, will have a lot to say about that.
Yeah, I mean, totally agree with that. I was also going to say the UK's and Europe is in quite a good position, actually, really. There's the UK programme, so some people might be surprised about this, was sort of predated any other national activity. So in 2013, the government, before any other person thought that quantum was even a thing, sort of committed £250 million of taxpayers' money into a programme to set up quantum. And that was before anyone really thought quantum was a thing. So they sort of realised that all this quantum research that was happening, a lot of science happening in universities, was sort of ready to become future products, so like sensing, communications and computing. So that's almost a decade now that the UK's been investing. And so there are lots of companies already in the UK, Europe, working together. there is this, it's sort of almost like a new supply chain that's forming, because we're all trying to build these completely new systems that surpass anything that's ever been done before. So on the photonic space, so ORCA and Aegiq build like new photonic. Photonic means light-based, so I don't know if everyone knows that. So we build quantum computers using light. So we take a supply chain, we take lasers that are already out there, take telecoms, laser systems, we turn those into single photons, so single units of light, which are what the quantum things are, and then we use those for computing. And Aegiq are making the sources that make these single photons. So there's already like a really
supply chain that is coming together.
Exactly, and that's not easy because we're all trying to work out how this all fits together. But at least those ingredients are there. And then the final bit is the skills piece, like getting the world's best quantum people together with the world's best machine learning people and computer scientists. And already Europe also has those ingredients as well.
So actually, that actually must be quite challenging, because if you probably are an expert in one field, then you probably don't know too much about another. And instead, in this big supply chain, you need the business expertise, but also knowing the tech. But then if you need to have extreme depth into the tech side, and you need to connect the dots, right?
The biggest bottleneck is the scarcity of talent.
Yeah, and I think to add on the education side of things, because so we talked about people who are like product developers in terms of talent and education, but there's also education on the kind of end user side, and the just being comfortable with the concept. I mean, it doesn't mean that they have to be like deep, quantum physicist or somebody to kind of embrace it, but it has to be the fact that they have this. It becomes something of a more common sense kind of thing, and then this is an education that like whole ecosystem has to do, like government, schools, universities. So if you mention that in a textbook somewhere, a list of promising technologies, everybody knows AI. They don't know what it is, but they know AI. Like, let's solve this with the AI. Yeah, throw it in.
Yeah, I mean, I remember somebody the other day on LinkedIn, we're talking about investment, and it was like, can't you use AI for that? And it's like, what? Sure, whatever. Let's use quantum and blockchain as well, why not? Anybody got a question, like we're in the last few minutes of the panel? Yes, please.
Yeah, just on your point about talent, how are you seeing the talent flow between different companies, but also between different countries and geographies in the world?
Good question.
Yeah, but it's not like, I mean, it doesn't flow so much because there's so little of them. That's the thing. So it's a proper people hunt that's going on. Part of why everybody's saying, you have to have talent. The obviously like visa situation, different rules, and not enough kind of ease of access is definitely a thing, for sure. So as everywhere else, but the marketplace is pretty small right now. So
very tight, yeah. I think in the UK we've done well to attract an international workforce. So if you look at the nationality list in our team, we're close to 200 people in the UK. It's very mixed. In fact, the English are a minority. But if you look at our teams in Germany, in Japan, or the US, it's very much localized.
By the way, I think we're hitting on time. In the meantime, I saw one question. Is it the last question? Are we switching over? No? Another question? Is got? Last person.
There's a question, please.
Huh?
There's a question, just feel free.
Perfect. Do you want to just announce it so that we can follow on?
Hi. This kind of like a two-part question, actually. So, bearing in mind, if you look at algorithms, say adiabatic or annealing or even VQE, they're fundamentally dependent on the representation of an Hamiltonian formation. Bearing in mind, you mentioned, for instance, machine learning. And fundamentally, it sounds like what you're talking about is the formulation of an objective function as a Hamiltonian. And we know there's a limited number of algorithms which are representable in that form, or alternatively look at Shor's algorithm. Fundamentally, it's really looking at periodicity in a quantum FT. To what extent do you think the limitations in representation ability of a program within the context of existing
guess I could answer that in a nutshell, in that I would say that quantum won't be useful for everything. And so to your point, part of the challenge with adopting quantum computing is you need to really look at a lot of problems to work out the types of problems where the structure or the Hamiltonian or whatever it is maps onto your quantum system. And that mapping isn't automatic. Like quantum isn't good for everything. It's only good for certain types of problems. Sometimes you have to restructure the data or the problem to be useful in the quantum computing. So the very short answer is that's the thing that everyone is on the algorithm side spending every waking hour doing at the moment, working out those problems and how they map.
Finding the problems and finding the right way to map it. Thank you very much for this panel, Waseem, Max,
Thank you.
and Richard. Big round of applause. And on to the next one, I think.